In this lecture, we look at the magnetic force on charges. A stationary charge Q feels no magnetic force due to a magnetic field. But a moving charge of velocity v does feel a force, and it has the form of F magnetic is equal to the charge times the cross product of v and b. The magnetic force is perpendicular to the velocity in the magnetic field because that's the nature of the cross product. If we have a charge Q moving with velocity v, and it enters a B field that's perpendicular to it, pointing out of the page, with this, as shown here, then if we do the cross product, we put our fingers in the direction of the velocity v. Our thumb then is, we curl our fingers in the direction of the B vector, and then our thumb will be pointing downward, which is the direction of the force. So initially the force is downward, but as the velocity changes, because it'll change direction, the force will remain perpendicular to the path. So the path will be this arc. Actually, it's a part of a circle, so a circular arc, and that indicates it's a centripetal force. So the charge Q will follow that path. The direction of the velocity changes, but the magnitude does not. If Q were less than 0, the force is initially upwards. So if our charge was negative rather than positive as in the first case, the charge would be sent upward. Well, even politicians know the right-hand rule, as we can see that Nancy Pelosi is using it in her discussion, and Obama is explaining this to a constituent, I guess. The Aurora Borealis is one of the most beautiful phenomena on Earth. It turns out that we can explain them due to the force of the Earth's magnetic field on charged particles from the Sun. If we look at a charged particle with a certain velocity v, if it was perpendicular to the B field, we've already seen that it would follow a circular path, but since it has a slight angle to it, this path turns into a spiral, as we saw there. So we have charges like to spiral around magnetic field lines. The Earth's magnetic field extends far out into space and will collect much of the charged solar wind. So here we have a picture of the magnetic field extending far out into space. We see the B field lines. And around the B field lines, we see spirals. Those spirals are charged particles that have come in from the Sun at some angle to those B field lines and get captured by the B field lines and brought down to the Earth's surface. And the charged particles are concentrated at the poles or in the north. These are also, the Aurora Borealis is also known as the Northern Lights because there are many B field lines coming into the North Pole of the Earth. The collisions of these high-velocity charged particles with the air makes the light of the aurora. It's as simple as that. The magnetic force does no work. The force is always perpendicular to the path or to the displacement. So work, which is equal to the force dotted into the displacement, is equal to 0. It's as simple as that. Let's look at some examples of magnetic force on an electron. In our first example, we consider a B field with a strength of 1 Tesla and an electron with a speed of 10 meters per second as shown to the left. Both vectors are in the plane of the paper. The right-hand rule gives the direction of the force on a positive particle to be perpendicularly upwards out of the paper. So if we do the V cross B, we see that V crossed into B, your thumb points out of the page, but the electron is negative, so the force is down into the page. The magnitude of the force is equal to the magnitude of the charge of V cross B. That's the magnitude of the electron's charge times the magnitude of the velocity times the magnitude of the B field times the sine of the angle between the two vectors. So that's 1.6 times 10 to the minus 19th times 10 meters per second times 1 Tesla times a half, because the sine of pi over 6 is a half. That gives us 8 times 10 to the minus 19 newtons. Not a tremendously strong force, but electrons are also very light. In our second one, we interchange the velocity and the magnetic field. Same angle between them. So the magnitude is unchanged. So it's still 8 times 10 to the minus 19th. But using the right-hand rule, the sign of the sign of the charge gives our directional force to be upwards of the page, because V cross B would point into the page, but now it's a negative particle, so it flips it around out of the page. And lastly, we look at the case where the velocity and the B field are parallel, so of course the force is 0. That's it.